Welcome to Grade 12 College Preparation Physics. Today we start with Unit 1, Motion, Kinematics. And today's lesson, lesson number 1, is entitled Distance, Position, and Displacement. Kinematics is the study of motion. It comes from the Greek term kinema, which means movement. All quantities in science can be described as either a scalar quantity or a vector quantity. Scalar quantities are those quantities that express only a quantity and a unit. And there are many scalar quantities that you might be familiar with. For example, time is a scalar quantity. An example of time would be 5 seconds. Mass is another scalar quantity. An example would be 25 kilograms. A third example is speed. And an example would be 100 meters per second. Each of these examples contains a measurement or a quantity and a unit. The first scalar quantity we're going to look at today is called distance. This may be a term you're familiar with. The official definition of distance is the path length an object has traveled. It is a scalar quantity, and the symbol for distance is delta D. Delta is a Greek letter that we put in front of a character, and distance is measured in meters. Here we have an example of an insect traveling from position A to position B, and it follows this curved path length. If you were to measure the length of this curved path, you would have the distance. So the distance in this example is 35 meters. So this insect traveled a distance of 35 meters. Note that there is a quantity and a unit. If a quantity is not a scalar quantity, then it must be a vector quantity. Vector quantities express a quantity, a unit, and a direction. And that's what sets them apart from scalar quantities. It's that vector quantities contain directions. So let's go through a couple of common examples of vector quantities. The first one is velocity. An example of velocity is 100 meters per second east. If you notice, this is similar to the quantity for speed. We said speed was a scalar quantity, and velocity is a vector quantity because it also includes a direction. We'll be speaking more about the difference between speed and velocity in an upcoming lesson. Another example of a vector quantity is acceleration. An example of acceleration is 4.0 meters per second squared west. Let's take a look at a couple of vector quantities that relate to this lesson. The first one is position. And position is defined as the location of an object relative to a reference point. And what's critical to note here is that positions always contain a reference point. Positions are vector quantities, so they contain magnitude, direction, and also this reference point, which sets them apart from any other vectors. They're the only vectors that we will be using that contain this reference point. The symbol for position is the lowercase letter d with an arrowhead on the top. Whenever you see an arrowhead on the top of a symbol, you know that it is telling you that it's a vector quantity. Another way to denote vector quantities is with just a straight bar over top, or some textbooks might actually use the bold letter D with no arrowhead on top to indicate that it's a vector. The unit of measurement for position is the same as for distance, and it's the meter. So let's take a look at the example with the insect. We have its initial position at point A, which we will give the symbol D with an arrowhead, and you can use the letter I as a subscript to mean initial. So in this case, the initial position is 0 meters from the start. The insect travels along that curved path that we described above and ends up at point B, which we will call the final position. And we will use the subscript F to tell us that it's the final position. And in this example, the straight line distance between point A and point B is 23 meters east of start. So we see that there is a direction and also a reference point. Two things that are required for the vector quantity position. Our next vector quantity that we'll look at is displacement. And displacement is defined as the change in position of an object. It too is a vector quantity. It contains a magnitude and a direction, but no reference point. The symbol for displacement is delta D with an arrowhead on top. So it's very similar to the symbol for distance, but this time, because there is an arrowhead on top, we know that we are referring to a vector quantity. Displacement represents the straight line segment directed from the initial position DI to the final position DF. And we have an equation that we can use to solve for displacement. Delta D is equal to D final minus D initial. It's our first equation in this course. Let's take a look at this example with the insect traveling. The insect travels from point A to point B, but the displacement is the straight line that joins these two together. The displacement would be this line right here. If you were to measure this out and it were drawn to scale, we could say that the position is 23 meters east. Know that you don't have to put a reference point when you're talking about displacement. It is the straight line that joins the starting position to the final position. Let's try an example. Sample problem number 1. Imagine that you walk from the school 500 meters east of home to the library 1,200 meters east of home in a straight line route. What is your displacement? Whenever you're handling a physics question, you want to read the question and write down what is given in the question. So let's take a look at what the question has given us. We're given this 500 meters east of home. This quantity contains a unit of measurement, a direction, and a reference point. Since it contains all three of these things, we know that this quantity is a position. More specifically, it's our initial position. The second piece of information that's given is 1,200 meters east of home. This is our final position, which will be given the symbol D with an arrowhead on top with the subscript F for final. Note, you can also use D1 for initial position and D2 for final position, you'll find that some textbooks and some questions interchange these both. The important thing to know is which comes first and which comes second. Okay, after you've done the given step and written down everything that's given in the question, our next step is to find out what they are asking us to do, what is required. And what they are asking us to do is to determine the displacement. So we need to find delta D with an arrowhead on top. That is the symbol for displacement. So you write down what you need to find. So let's analyze what equation we can use. If we look up above, we can see that the equation for displacement is final position minus initial position. So let's sub in our values and solve. Sub and solve. So delta D is equal to D final is 120 meters east of home. 1,200 meters east of home. And from that, we are going to subtract the initial position, 500 meters east of home. So here we've set up an equation that looks like we're subtracting 1,200 meters east of home and 500 meters east of home. Whenever you are subtracting vectors, you need to know an important rule. When adding or subtracting vectors, all directions must be the same. And if they're not the same, I'll show you what to do. In this example, we're subtracting 1,200 meters east and 500 meters east. Both of these are the same direction, so we can just proceed and subtract these algebraically. That means take out your calculator and do 1,200 minus 500. If you punch that into your calculator, you should get delta D is equal to 700 meters east. Note, when you find the position, or the displacement rather, you need the measurement, the unit, and the direction. There's no need to put in the reference point when you're talking about the displacement. Okay, let's try sample problem number 2. We're going to use the same diagram above. In sample problem number 2, it says, what is your displacement if you walk from your school a position of 500 meters east of home to the mall a position of 1,000 meters west of home? So I'm going to start by writing down what's given. The first thing that's given is our initial position, and it's 500 meters east of home. Our final position is also given, and it's 1,000 meters west of home. Note that I wrote down what was given in the question, but I didn't write the word given down. You don't have to write the word given, but you cannot skip this step. This is the most important step, finding out what they want, what is given in the question. The second most difficult part of any physics problem is the second step, which is finding out what they want from you, what is required. And again, you don't have to write these words down, but you cannot skip this step. In this question, what they're asking us for is, what is your displacement? So what they want us to find is displacement. So let's analyze which equation we'll use. We have the equation displacement is equal to final position minus initial position. And remember, it's important to know which one is the final and which one is the initial. You cannot mix these two up or you'll get the wrong answer. So let's write down the values. We'll sub and solve. So that's 1,000 meters west of home minus 500 meters east of home. Now remember up above when I told you that when you're adding or subtracting vectors, they have to be in the same direction. So the same has to be true here. When adding these together, they must be in the same direction. Here we have west, and here we have east. We have to either express both of these as west or both of these as east. So how do we do that? Well, here's a trick. You can switch a direction by switching its sign. Now, in order to add or subtract these, west and east must be located along the same straight line. And west and east are located along the same straight line. They're just in different directions. So what I want to do is change both of these to west. So the first example, there's nothing to change. It's 1,000 meters west. Now the second example, "500 meters east of home," which we are subtracting, I want to make it west. And when I make it west, you have to switch its sign. So 500 meters east of home is going to be negative 500 meters west of home. Just move this closer here. So we have 1,000 meters west minus negative 500 meters west of home. So initially it was 500 meters east of home. I've changed 500 meters east of home. I've changed this part right here, 500 meters east of home, to negative 500 meters west. Now, I just want to tell you this. 500 meters east is equal to negative 500 meters west. They are the same thing in physics. So all you do is switch the sign and you switch the direction. So now you can punch this into your calculator. 1,000 meters west minus negative 500 meters west. Keep in mind, if you have negative and negative together, as we do in this example, you're going to end up with 1,000 meters west. These two negatives come together to make a positive 500 meters west. These are in the same direction now, so we can add them on our calculator. And folks, make sure you use your calculator whenever you're doing calculations in physics. I don't want you to lose any marks because you tried to do the calculation in your head. There's no shame in using a calculator no matter how simple the question is. So 1,000 meters west plus 500 meters west is 1,500 meters west. And that's your displacement when you walk from your school to the mall. Okay. Your job is to try these homework practice problems. I will provide you with the solution so you can check your answer. And in addition, there will be a quiz for you to perform on the LMS site for our class. Good luck.